Let's take this black point in polar coordinates, and I'm just going to move it around anywhere I please on the plane. I'm going to spin it around the origin or move it as far as I want from the origin, right? So we just have this black point, nothing special about it. Now, what I'm going to do is I'm going to add a second point in which that point is rotated an angle phi, or any angle away from our original point. So first we have our black point, that's our starting point. And notice this red point is going to be rotated, the original point rotated a certain amount of an angle away from the origin, right? There's nothing too significant about what we have here. We know that this black point is going to have coordinates in the polar plane, as it's going to have a radius away from the origin and an angle from 0 degrees. And the red point is going to be that same radius with the original angle plus the angle that we added. What I'm going to do now is switch over to rectangular coordinates, and then I'm going to attach coordinates to these points. So for our original point, given the polar to Cartesian translation, our original point is going to have coordinates the radius times cosine and sine of theta, and our translated point, in which we rotate our original point, it's going to have coordinates r times cosine of theta plus our original angle, because remember, we just move theta and then move an extra angle over here. So these are coordinates in the rectangular plane. So in general, we know that if we have a point and we want to rotate that point an angle clockwise about the origin, we know that the resulting point is going to have these coordinates. For example, if I start with our point at lying on the x-axis and I rotate 90 degrees about the origin, I'm going to end up on the y-axis here. So if this was 1, 0, this would be 0, 1. Thing is, what if I move my point here to some random angle that we don't know? It's going to have some pretty not nice coordinates and probably going to be irrational. The question is, can we find a general solution for getting the coordinates of a point that results from rotation about the origin? The thing is, we can actually do that. And today we're going to talk about rotation matrices. And these are matrices such that you can multiply it by a vector, which is basically another matrix, which represents our point. And the result of that multiplication will be another point that represents rotation about the origin. So we have our points P and P prime. This is just a point and we're rotating it an angle phi around the origin clockwise and resulting in P prime. So let's represent our points by column vectors with x and y coordinates. So it's going to have values in this 2x1 matrix, and that's just going to represent our point. What I'm saying is that there is a matrix R, or what I'm claiming is that there's a matrix R such that we can multiply by our column vector, which represents our point, and that multiplication is going to result in another point that represents rotation of our original point. That's a claim that I made. Now, first we have to prove that such a matrix even exists, and then if it does exist, we can find what exactly it is. If we have a matrix, it's going to have dimensions m, it's going to have m rows and n columns, so it's going to be an m by n matrix. Our column vector is going to have 2 rows and 1 column, so it's going to be a 2x1 matrix. And what we want is this multiplication to result in a 2x1 vector or matrix. The first thing when dealing with matrix multiplication is you want to determine if the multiplication is actually defined. And for matrices, for matrix multiplication to be defined, if you have, in our case, if you have m by n matrix multiplied by a 2x1 matrix, these inner numbers have to be equal to each other for the multiplication to even work, or for it to happen. So we know that n has to be equal to 2. Next, we're going to look at what we want to get from this multiplication to determine what m should be. So if you understand how matrix multiplication works, you'll find that m has to be equal to 2 to result in a 2 by 1 matrix. The outer numbers are what you get as a result of the multiplication, and the inner numbers are what determines if the multiplication will actually happen. So again, n has to be equal to 2, and m has to be equal to 2 as well. So our rotation matrix R is going to be a 2 by 2 matrix. We've established that, and that the matrix actually exists. Now that we've established that this rotation matrix actually works, I'm just going to write the multiplication out in terms of the elements that we're using. So instead of the matrix R multiplied by our column vector representing x and y, I'm going to write R in terms of its elements. It's a 2 by 2 matrix, so it's going to have 4 elements. And then x and y, I'm actually going to write it in terms of its polar coordinates because we're dealing with rotation, so polar coordinates would be the easier choice in this situation. Now that we've written out the rotation matrix R multiplied by our vector xy, I'm simply going to perform the actual matrix multiplication that is happening here. So remember, with matrix multiplication, it's just multiplying the first rows by the second columns. So we have this first row multiplied by the columns that results in this first resultant row. And then we have our second row, or next row, multiplied by the same column, and we have our second row. So that's this entire multiplication. And remember, the actual multiplication is the dot product. So we have R1 times this, R2 times that, R3 times this, R4 times that. And it results in this 2 by 1 matrix. Also note that I just factored out our R, which is our radius, and it shows up in all these terms, so I just factored it out to make the process easier. After expanding R times xy, I'm going to go back to our point that we're looking for, which is P prime. It's going to be the matrix that represents our resultant point after rotation. So I'm also going to write point P prime in terms of its polar coordinates. And the only thing that changes from our original point is that there's an additional angle added to it, and we're calling that angle phi. Our original angle is theta, and then we add phi. So it's going to be r cosine theta plus phi, and so on. What we can do with this addition is that we can actually apply the cosine and sine angle addition. Again, I factored out the r because r is in front of all these terms, and it's going to make our process easier. But another thing I also made it easier to note is that I have our terms with theta on the right side of each term, and the coefficients are going to be terms with phi. And you'll see how that works in just a second. So what I've done here is I have this matrix, which also equals this matrix. And our objective is to find this matrix here with R1, R2, R3, and R4. So given that these two matrices are equal, and one of them contains R1, R2, R3, and R4, we can actually find each of R1, R2, R3, and R4. How I'm going to do that? First, I noticed that these are both 2 by 1 matrices, so I'm simply going to compare the respective positions in each matrix. So I realized that I had a mistake here. This is supposed to be a sine theta, but it'll still make sense. So what we have is R1 times cosine theta, or we have something times cosine theta plus something times sine of theta. And on the other side, that's equal to something times cosine theta plus something times sine of theta, because subtraction is basically addition. They're one and the same. I think now I can reasonably assume that R1 is equal to the same something times cosine of theta, and R2 is equal to the same thing multiplied by sine of theta. They're being multiplied by the same thing, and they're equal to each other. So I'm going to make the assumption that R1 and R2 are equal to cosine of phi and negative sine of phi, respectively. Same thing for our second row. We have R3, or something times cosine theta, and something times sine of theta is equal to something times cosine theta plus something times sine of theta. So now I'm going to say that R3 and R4 are equal to sine of phi and cosine of phi. What I've claimed is that I've now found all four values for our rotation matrix, which are cosine of phi, negative sine of phi, sine of phi, and cosine of phi. And I'm going to put this, imagine this is just a 2 by 2 matrix. This is exactly how they're going to show up in the matrix in these positions. So I don't feel like writing it all again. But this is our rotation matrix, or I claim it's our rotation matrix. And I'm going to show how this actually proves true. What I've just claimed is that I found a matrix that I can multiply by our point to result in rotation. So to prove that, I'm just going to do exactly what I did, but in Desmos. So first we have our matrix representing our original point, point P, with xy coordinates. I have the point actually plotted on the plane. And then I have our rotation matrix, our supposed rotation matrix, with the four values that we just found. And then because Desmos doesn't actually do matrix multiplication, this is just the manual values of the matrix multiplication between R and our original point. And I claim that this matrix representing our resulting point is going to be rotation of our angle phi from theta. So to prove that, I'm just going to move our angles. So I change our initial angle, and boom. Yeah, it works. So I'm moving our additional angle phi from theta, and yeah, it's the same distance from the origin, just a different angle. So yeah, hopefully this proves that rotation matrix, when multiplied by our point, actually does give rotation. Who would have thought? So how do we actually use this in real life, and what are the actual implications of a rotational matrix instead of just taking a point with a radius and an angle and adding an angle to it? So one thing I want to talk about is robots. If you didn't know, robots, they store position and they keep a record of their position, usually by X, Y, and Z coordinates. And robots, like if you take your arm, there's a lot of rotation. And so rotation is necessary for a lot of robot applications that we use today. And what robots do is they actually multiply the matrices in which they store their current position by a rotation matrix. So I have a demo here that I found online on Desmos, and it's not exactly a robot, but it's a really cool application of rotation matrices in the 3x3 world. A rotation matrix in the 3-dimensional world is just a 3x3 matrix. Same thing for 4 dimensions, n dimensions, it would be an n by n matrix. What's different with 3 dimensions is that there's 3 different types of rotation. There's rotation about the z-axis, the y-axis, and the x-axis. In the plane, there's only rotation about the origin. There's not many things you have to consider, but in 3 dimensions, there's more individual rotations. And the last thing I want to show y'all is just a really cool demo of what this looks like. So I'm just going to spin this cube. Yeah. So hopefully this showed y'all that we can actually multiply a point by a matrix to result in a point that will represent rotation. That doesn't really make sense when you think about it, because how can we multiply a value by one thing and result in rotation? That doesn't make sense. Usually we just add an angle and that's it. But no, once we expand to matrices which hold several ideas or concepts in one, we can do things that we couldn't usually do in Cartesian or polar geometry.